Alright, in this video we are going to talk about the next topic, which is stress and strain. Okay, stress and strain. So stress is about the force. Okay, it's something related to force. You know, pressure back in thermo 1, pressure is force over area, right? So stress is also force over area. Okay, this force is, for example, if you have a structure, okay, this is your structure, and I give this structure a pull, right? A pull on both sides of the end, right? On both ends, I give it a pull. This pull is a pulling force, okay, and this is the force that you're talking about, F. Okay, but what about the area that you're looking at here? The stress that this pen is experiencing is the pulling force divided by the cross-sectional area of this pen. Okay, so to put it very simply in a diagram, when you have an object, okay, and it undergoes we call this a longitudinal pull, okay, along the longitudinal pull, the stress experienced is the force, okay, and you're going to find out that these two will always be the same. Okay, these two forces is the pulling force will divide by the cross-sectional area of the object. Okay, the area that is actually perpendicular to this force. Okay, so let's say there is a force acting here, right? So the perpendicular area is this one. Okay, so this is how you define the area. If you have a rod, okay, if you have a metal rod, you are pulling it this way, the area is the area of the circle. Okay, it doesn't mean only pulling force, pushing force also can. So when I push, I compress, I do a compression, the stress can also be calculated this way. Okay, and the pulling force is just the tensile force, okay, the tensile stress. Well, if you give it a push, it is a compression, okay, compressive stress. Okay, so that's the main difference lah. All right, but the formula remains the same, F over A. Okay, next, strain. Strain is related to the elongation. Okay, because this object, right, will always deform. Okay, it will always change in its shape, right, change in length in this particular case. So originally, if your object is this long, okay, and then you pull it like this, what's going to happen? It's going to elongate, right? So maybe you will the total length will become like this. Okay, the new length after I pull, the new length will become like this. Okay, so what does it mean? It means that from here to here it has increased in the length, right? Okay, increased by how much? This is the difference. Okay, this is the difference, this is the elongation. Okay, and for elongation we call it X. Okay, elongation is X, and the original length is always called big capital L. So how much it is being elongated when it is undergoing a pulling force. Okay, so this is the X, this is the L. So the same as compression, if you have a pair of forces pushing it in, right? So what's going to happen? It's going to compress, right? The object is going to shrink in length. Okay, so it shrink in length, right? So this much is your what do you call it? Shortening lah. Okay, so instead of elongating, it shortens. Okay, so this is your X. So these two X have the same meaning. Okay, and the original length is this L over here. Okay, so how much strain is happening is we call strain this curly E okay, is actually defined as X over L. Okay, how much the delta, how much change over the original length. Okay, as for stress, we call this a sigma. Okay, sigma it's a Greek letter sigma is equals to F over A. Okay, so these are the two main formulas that you'll be looking at. Okay, stress over strain. Yeah, stress and strain, sorry. And of course, there is a thing called stress over strain. When we divide stress with strain, right? Okay, this is actually your Young's modulus. Okay, Young's modulus. You may have seen this in your materials module, Young's modulus. Okay, this one is how strong is your material. Okay, for example, if you compare between aluminum and stainless steel, okay, the E of stainless steel will definitely be higher than aluminum. Okay, so you may remember this one. This is let me see, stress, and this is strain. Is it? Yeah. And then you have this this curve. Okay, so this part is the elastic portion. Okay, elastic region, where the Young's modulus is the gradient of the line. Okay, and when your material hits this region, right, it starts to become plastic, and then it may never go back to the original shape anymore. Okay, something like that. But we don't have to go to that topic. Okay, we'll just look at E is equals to stress over strain. Okay, and in your questions, in your tutorial and your tests, questions will always be asking you about what is the total elongation. Okay, total elongation. Okay, and then you'll be asking about X. Okay, so it is let me see. Okay, let's talk about this later on, but the idea is this: how do you express X in terms of all these terms? Okay, you know that strain is equals to X over L, right? It's X over L. So X is equals to strain times L. Okay, so this is strain times L. Then you also have stress over strain is equals to E, right? So what is your strain? Strain is actually stress over Young's modulus. Okay, so you put this one inside here. Stress over Young's modulus multiplied by L. Okay, you're going to use this formula very often in your question. Later we will see. Okay, we'll talk about it. Last but not least, okay, quite important is your factor of safety. Okay, the whole topic, the most important part for an engineer is the factor of safety. Okay, first of all, let's look at the formula. It is actually your yield stress, okay, which means the stress which your material will sort of break, okay, not perform as you expect. So that is the maximum stress that it can hit. That's the yield stress of the material over the working stress. Okay, working stress is something like you design something, and then when you apply a load, right, that kind of stress that experienced by your design, okay, what is the value? That is your working stress. Okay, let me give you an example. If your boss, okay, asks you to design a chair, okay, so you design a chair, okay, you design a chair using a certain material. So let's say your certain material that you use, the yield stress is say 10 megapascal. Okay, you use a certain material, and then your boss will ask you, hey, what is your factor of safety? Okay, when under what kind of condition? When a certain person, okay, when a person sits on, of course, when a person sits on the chair, okay, then there's a load, right? And then there's a load. Because of this load, there's going to be stresses experienced by the whole chair. Okay, so maybe the stress at this point, okay, will be say 1 megapascal. Okay, and then maybe the stress at the legs, right, is different. Maybe the stress at the legs give you 4 megapascal. Okay, and maybe the stress at this part is say 2 megapascal. Okay, once the person sits down, you can actually measure somehow measure out the stress at the different location. Then what will you report to your boss? Boss, my design has a factor of safety of what value? Okay, now of course let's look at the three options. If you use 1 megapascal, so what will your FOS be? You know is 10, so it's 10 over 1. FOS is 10. Okay, if you use 2 megapascal, so your FOS is 5. Okay, if you use the stress is 4, what's your FOS? 2.5. Okay, you see the effect here. By taking different stress, you have a different FOS. So what will happen if you tell your boss, I have FOS of 10? Wow, then your boss will be very happy, right? Wow, your design is so safe. Means what? Means you design so well that it won't break very easily. Okay, the factor of safety is so high, means it's very safe. Okay, but are you telling the truth? Okay, that is the question. When you sit down, the heaviest load is actually here, right? 4 megapascal. So the factor of safety at this location is only 2.5. So the correct reporting to your boss should be, boss, the chair's factor of safety is 2.5. Okay, so this should be the correct answer. Always use the highest stress into this formula. Okay, now let's see how it works now. Everything come in. Tutorial question. Let's look at question 9. Okay, this one is about the brass rod of 500 mm long. Okay, being milled down at both ends. Okay, so how's it going to look like? Brass rod, okay, means it has a circular profile. Okay, milling, you know, milling, turning, sorry, it's being turned down, means the end, both ends are going to have their diameters decreased. Okay, okay, so both ends have a smaller diameter. Originally the whole thing is a constant diameter, but because of the turning operation, right, you turn here and then you also turn here, these two parts, the diameter, right, shrink to a smaller diameter. So that's how it becomes. Okay, so total length is 500, right, but 100 on each side, so the center part is 300 mm. Okay, both ends is 100. So that's how it looks like. Okay, so this diameter is 20 and both sides diameter is 15 mm. Okay, we can do this way. Let's call this section 1, section 2 and section 3. Okay, and you know that the axial pulling, so there's a pair of forces pulling. Okay, this force is 7 kilonewton, which is 7,000 newton. Okay, so it's going to elongate. Okay, so 3 different parts okay, they have different diameter. So what you can see is that this section will elongate by a little bit. Okay, maybe this much. This section will elongate by a little bit. Okay, and this section will elongate by a little bit. Okay, So your ideal total elongation is elongation at 1 plus 2 plus 3. Okay. So total elongation equals to x1 plus x2 plus x3. Okay. Basically this is it lah. But there's one good thing here is that both ends have the same diameter. Okay. Since they are same material and same diameter, you're gonna have the same elongation. So in fact, we can combine x1 and x2 into combine together to become 2x1. Okay, because the x is going to be the same. Okay, and then the center part is just you need to find lah. All right. Okay, so remember just now I mentioned that you are going to use this formula. Okay, x is equal to sigma over E times L. Okay, so here you're gonna use it. Okay, x is equals to sigma over E times L. Okay, the sigma is the stress at this part. E is the same because E is related to the material, right? And the material here, whole thing is brass. So the E for all the parts is the same. So Young's modulus of brass. The length is this length. Okay, is the length of the third part. So L1. Okay, and you multiply by 2 because there are two ends. Okay, now let's look at the center part is sigma 2 stress experienced at the center over E of the brass multiplied by the length of the center part. Okay. Yeah, so let's go. So 2 sigma. Okay, sigma. How do you find sigma? Force over area. The force that is being experienced by the whole rod is the same, which is 7,000. Okay, so the force is 7,000 over area is the area of the 15 mm diameter. Okay, so area of circle is pi d square over 4. So pi over 4 d square. Diameter is 15 mm. Let's convert to meters. It will be 0.015 square. This is sigma 1. Okay, this is sigma 1. I still need to divide by okay, let's not do this. Divide by Young's modulus, 90 gigapascal. 90 times 10 to the power of 9. Okay, giga is 9. So okay, let me write this again in a cleaner way. 7,000 over pi over 4 d squared, 0.015 square over Young's modulus, 90 times 10 to the power 9. Okay, multiply by the length of the rod here, 100 mm. Okay, which is 0.1 meters. Okay, so this will take care of the elongation at both ends. Okay, times 2. Okay, and then you're gonna have the one at the center, 7,000 over pi over 4 d 0.02 square. Okay, divide by 90 times the length of the center part is 300 mm. Okay, 0.3 meters. Okay, so that's the total elongation. Okay, you should be able to get let me see 0.000162 meters. Okay, which will be 0.162 mm. Okay, now factor of safety, part B, factor of safety. Okay, yield stress over working stress. Okay, yield stress is given in the question, 190 megapascal. So 190 times 10 to the power of 6. Okay, this. Now, what do you use for your working stress? Okay, at both ends the stress at both ends is this one, force over area, this one. The stress at both ends is the same value, this one. The stress at the center is this one. Okay, so like I said, the guiding principle is you must use the higher value of the stress with the higher value. So the stress at the end has the higher value, so you should use this value. Okay, you should use the stress at the 15 mm diameter. Okay, and if you calculate, this value is actually 39.61 times 10 to the power of 6. Okay, so this is your stress here, 39.61. Okay, and you will find that your factor of safety is 4.8. Alright, so that's how you do a typical stress strain question.